Good evening, everyone. So as Prof mentioned, I'm just going to give a bit of a brief tutorial this evening on the topic of causal inference. All right, so this is actually a pretty complicated topic. I'm just going to go over some of the basic concepts and some fundamental methods in the space of causal inference that kind of just get your feet wet in the area a little bit. It's an area that I think, especially in with the data science, it's useful to focus on because they're problems that are probably better tackled through this lens of causal inference than under the standard like forecasting, predicting paradigm that we're more accustomed to using. Okay, so oops. Okay, so just overview. So I'm just going to give an overview of causal inference, like what I mean by causal inference, what is causality, stuff like that. Then I'm going to go over a bit about the Rubin causal model, also called the potential outcomes model of causality, and just describe some of the important ideas there and how these ideas then, and then in part 3, I'm going to discuss how these ideas then come to the fore and actually, to some extent, in terms of actually trying to perform causal inference on observational data. Right. So a large subset of human knowledge can be described as causal. In other words, like things like example, X causes Y. And in some cases, this is probably one of the most important subsets of human knowledge. It really is, to build these causal models of the world and being able to reason using these causal models of the world. In terms of deciding like how should we solve different problems, right? And there are two types really of causal knowledge that you find. There's something a bit more in the philosophy literature, but I will say it's kind of important computationally, and that's what you call type causality. So that's actually concerned with more general relationships between different categories of objects and events. So for example, we know that repeated exposure to high levels of asbestos, it tends to predispose people towards developing mesothelioma, which is a fairly rare type of lung cancer. That is an instance there of a bit of knowledge that would be considered a form of type causality. So it's referring to two generic or general types of events and the relationships between these types of events. Then you have token causality. In philosophy, they like to use the term actual causality for it, but personally, I really don't like that term. And this is more concerned in terms of reasoning between causal relations between different specific instances of objects and events. So, for example, you say that Tom worked in an asbestos mine for a couple of decades, and then this might have been led to him developing his mesothelioma. So it's like a specific instance. It's not, Tom is a specific person, right? And so this is an instance here of what's called token causality, right? The ability to reason. In some extent, it's like taking like type causal knowledge and then being able to take other pieces of information there and actually then start to reason behind like what's causing certain things under certain different situations, right? And type causality can be considered to be, to some extent, the main and chief objective of science, in a sense, is that we want to build, I suppose, these causal models of reality that we can then use in engineering tasks to actually achieve different aims and objectives, right? So much of science we consider this type causality here. Right now, of course, there's the old adage essentially that association is correlation is not causation. Or you can say like association on the whole on its own is not just it's not sufficient for determining causation. For example, you see like the picture of that cat there. I mean, I doubt that cat caused that roof to bend, right? So that's just a humorous example there. The association on its own is insufficient to indicate causality. In philosophy, there's this particular It's actually a particular logical fallacy, post hoc ergo propter hoc, literally after this, then because this, that is regarded as a big no-no in terms of reasoning, right? So you say, of course, of course the cat didn't cause the rooster to become dented, but the thing is, like, this is just an example here of a more subtle issue that can sometimes slip into human reasoning and to slip into when we try to actually build and determine causal relationships. That we have to be very, very careful, because associations can be quite misleading, right? As rules adage from statistics goes, correlation does not mean causation in general. So an example of this which can kind of come up in a sort of scientific context is this idea of these instances of Simpson's paradox, where, if example here, if you look on the graph on the right, there appears to actually be a positive correlation or positive relationship there between cholesterol and exercise, and that would give one pause, because they'd be like, okay, this really doesn't square with what we would actually expect, right? We'd expect, okay, the more you exercise, the lower your cholesterol levels would be. And it turns out that if you actually look, if you actually start to split up the units in your data set by their age brackets, you actually recover the sort of negative relationship, that negative causation that we'd actually actually expect to see. So it's like, this is like a case here where you have to be like, example of like, where this mindset of causal inference can be useful, because just to look at the data, if you don't look at it carefully, you can get easily misled, right? Now, of course, what's actually happening here is that in this particular case is that age has an effect on your base level of cholesterol. It will have an effect on the degree to which exercise can help, and they have an effect on the amount of exercise you can actually even do. So because age, so in a sense, like what we want to check there would have been the relationship between exercise and cholesterol, right? But you have age, right, which is another component of the units under examination and treatment. This impacts the exercise and also impacts cholesterol, right? So you have this case here where yes, exercise can possibly impact cholesterol, but you have age impacting both. So you have this case of confounding, and these sort of cases here of confounding can really be misleading, and can pretty be a frustrating to sometimes deal with when you're trying to actually uncover complex, or rather uncover causal relationships in complex data sets. Now, when we account for age, when we try to account for the confounder, we actually observe the pattern that you think is much more likely, which is that you see this negative association. The more you exercise, the lower your levels of cholesterol, right? Now, this is why we actually use randomized control trials. The idea here of randomized control trials is that we can actually abate the effects of confounding through random assignment. And provided we do it well, it can actually work out well in terms of isolating certain causal relationships. But it's actually sometimes it can be quite difficult to actually do randomized control trials well. The subtle relationships between treatment, i.e. our X, our antecedent essentially, and the covariates of our units under treatment. Sometimes as well, RCTs actually require you to actually design the experiment and run the experiment. And of course, that takes time and money. But and that's a lot more difficult than just collecting observational data or just using observational data that's already out there. And sometimes there are cases when observational data is like literally all you have, really, all you can actually get. And then there's this interesting point actually that it's actually a point has been raised by Judea Pearl, which for those who have a bit more of a background, some classical AI, you kind of remember that name as he's a Turing Prize Medal winner, but actually for his work on making causality computationally tractable under different circumstances. And he has raised an interesting point that sometimes these pretty artificial laboratory conditions, sometimes might not always might not, sorry, always be the best in terms of looking at these sort of complex causal relationships in these complex systems. We have tons of interaction between different aspects, different features, and different things, and these open systems and the like, right? So so we can't just throw, say RCT for everything in terms of trying to identify causation, despite how much we might like to, we just can't, right? Causation is important. No, I don't want to kind of like, sometimes there's this movement that, I've been seeing sometimes within data science community that people is like, or just forget, standard data science and ML types of causations with that. And I disagree with that, because there are some circumstances where you really don't want to approach things through a causal lens. So let's say, for example, we just care about predicting someone's cholesterol level, then, just the EH and exercise on its own as just inputs might be useful. We don't really have to care about the confounding between the age and the exercise, the cholesterol, etc. Because all we want to do is predict, does this person have like high cholesterol? We don't really care about designing intervention, and sometimes you don't really care about design intervention. Then this more forecasting oriented mindset is still really useful. It's still a very powerful tool. Depending on the overall problem that you want to solve, right? But let's say, for example, we want to now design interventions to try to reduce cholesterol, right? We actually want to do something out there in the world using this, try to use the data to help give us an insight to what we ought to do to solve a particular problem. Then that is where this causal paradigm becomes a lot more useful, right? So just also to kind of press, but you also want to take into consideration your objective and your aim. That is always something you keep in mind, right? That each of these different sort of paradigms of how you can approach data science, they have their relative merits under different circumstances. Okay, so let's actually discuss the potential outcomes framework. Now there are other frameworks and other ways of looking at causation. For example, I just mentioned Judea Pearl, and of course, a lot of his work, particularly there, would have been useful, with Bayesian networks and the like, and do calculus and the like. His stuff, I mean, of course, there is ML applied using that, but that's to some extent a bit more a domain of a more classical kind of AI in a sense. So I kind of want to look at things more stats oriented perspective to some extent. And this is through Rubin's potential outcomes framework, right? So before before we start to do like an attempt to actually start to assess and to test causal relationships, we need to actually start to build like appropriate formalisms before we actually put maths and computational power behind trying to actually assess causality. The Rubin potential outcomes framework is a nice formalism because it actually helps us rigorously capture some intuitions behind causality, and it also allows us to leverage some insight and some ideas of statistics and ML and probability, right? So the interesting thing there how behind the Rubin causal model is the kind of intuition kind of builds up. So like it kind of almost acts like to some extent it kind of sees causation in almost a counterfactual way. So what I mean by that is that, like say for example, if I drink this water, and then I say in another universe, I don't drink this water, then there's actually that universe one that's counterfactual to this current universe. So you can imagine, let's say someone, they have a headache, and so they just take, 1,000 milligrams of paracetamol, and the headache dissipates within an hour. And then let's say you have this other universe where this person decides, okay, they're not going to take the paracetamol, and the headache persists beyond 1 hour. And let's say, for example, these two universes, aside from this single action of this person taking this paracetamol, that these two universes are identical, right? What we'd say about the paracetamol and curing this person's headache is that the paracetamol helped this person with their headache, right? Because all else being equal in these two universes, the paracetamol is a deciding factor there, right? So like in a sense, Rubin's potential outcomes model it kind of asks us to pretend, at least in terms of trying to define what we mean by causation, what we mean by what we want to examine. Like it tries to have access and kind of pretend as though we're like the watcher from Marvel's What If, right? What if we can see into different universes, right? What if we weren't bound by human limitations and we can peer into other universes? Like how would we kind of conceptualize causation, right? So that's kind of like how this is pretty much like how the Rubin causal model, how definitions kind of come about, and we're going to kind of just kind of keep that in mind. I know that could be a little bit funny to kind of think about, right? But just try to just keep this in mind. Like we can imagine that we can kind of see into other worlds, so to speak, right? And I say this allows us to treat these things that we're looking at as sort of like random variables, and then we can apply some of our usual statistical ML and probability tools to it. All right, so we can say we have n treatment units. We have a bunch of these different units. Use the usual subscript I. Let's for example, x sub I are the covariates as features for treatment unit I, and big X is the matrix of those covariates as features. T sub I is the treatment afforded to unit I in our current universe, right? And T is a vector of treatments, and Y sub I is the outcome of treatment T sub I on unit I, right? That's in our current universe here, right? And remember, we can imagine, we can see in the universes where we treat this person versus not, treat this unit versus not treat this unit, right? So and we have our current universe where we apply a treatment to the universe and we see the outcome, right? But we could also peer into the universe where we performed the opposite, right? Where if this is a treatment in our current universe, we see the universe where this unit was a control. Where if this is a control in our current universe, we see the unit when it's treated, right? We can see that. Let's imagine we can see that. So for example, here we're saying, okay, unit 1, in our universe that they were control, right? And their outcome was 0. But we can also peer into that universe where they were treated, and they had an outcome of 1, right? So the difference between treatment and not treatment for this unit is 1, right? We could proceed likewise for 2, 3, 4, 5, and 6, and so we have our differences here, right? Now, one thing to note, notice that, let's say for example, for unit 1, we didn't treat, and the outcome without treatment and the outcome are the same, right? Like let's look at unit 2, we did treat, and the treatment when given the outcome in our universe and the outcome in the universe where we treat are the same, right? So that's just an important thing there, just to kind of keep in the back of your mind when we go through some of the basic proofs that we're looking at in a bit, right? So with this, imagine if we could just have this sort of table here, kind of describing our describing the multiverse essentially. And what are some things you might want to calculate based off of this? So you might want to calculate, okay, what is the individual treatment effect? So this is pretty much like for a particular treatment unit, what's going to be the effect of the treatment on this particular unit. But I mean, this is all well and good, but what we care about to some extent is like these type cause relationships, right? So we want to care about like what's the average treatment effect. So what do we expect the difference to be overall, right? So that could be like just the average of this difference column here. Another important one is the conditional average treatment effect, or the CAT. And this, we don't have any covariates listed here, but we might also want to try to get given different treatment units with different covariates, what is going to be the average treatment effect, right? And then we have the average treatment effect on the treated, which is pretty much only a subset there that were treated in our current universe. What was the effect of the treatment on them alone, right? So these are using this framework here. This we can define these useful statistical quantities that we can estimate. So we basically take these causal concepts and we map them to statistics we can statistically estimate, right? Now, what is one issue here And the issue is in our world where we are limited human beings, right? We can't just rip apart the fabric of reality and take a look at another universe. We can't see those other universes, right? So our real world tables look more like this, right? Just a bunch of those question marks, right? And we can't even calculate this difference here, right? So it's like how, okay, so what do we really go for there, right? So if we can't calculate these quantities directly, right? And the fact that we can't calculate these quantities directly because we can't pair into alternative universes. This is what we call the fundamental problem of causal inference, right? Now you may ask, okay, and this kind of goes back here. Well, of course, you know, we discussed like correlation a bit earlier, but like, can we just use a social difference? And the answer, of course, which is just correlation. Essentially, his answer is no. And let's just look at why, right? So the social difference here, it'll be the difference you can think of as the difference in the expectations of the outcomes conditioned on treatment and control, right? So you know, we obviously, because we're only restricting it to the treated units and untreated units in the two terms there, we can expand that out. And let's just add back in the counterfactual for the for the treated units, right? So add and subtract it back. So like on the second line there, we have plus the expectation of y sub naught condition on treated. That's the counterfactual for the treated units where in a universe where they weren't treated, right? And now once we group things back together, exploit linearity of expectation, we get a term on the left hand side, and this term is actually just ATT, right? So this is a valid causal quantity, but then look what we have there on the right hand side from the second and third term is that we have this expression here, right? And this expression here is actually the reason why association is not causation. It's because of this term there, it's called causal bias. Because if it wasn't for this term, we would actually be able to say association is causation. But it's because of this term here, which basically says that there's a risk that the two groups, the treated and the untreated, are different in their base level characteristics, right? And it's because of this is why the fundamental reason, at least under the Rubin causal model, why association is not causation, right? So the idea there then is there a way that we can get this term to zero? And if we can't get to zero, can we at least get it as close to zero as possible, right? So can we ensure that treatment units differ only in the treatments they are assigned essentially is really there? So, of course, like, this is where RCTs, of course, come in, because RCTs in an ideal world are a way to actually get rid of this causal bias, right? But as we know, these are not always possible, right? So there are actually 4 criteria you need to actually have, and if you have these four criteria, you can actually make this zero, get it close to zero. So first is exchangeability. So exchangeability is pretty much saying that the potential outcomes are independent of the treatment condition of the covariance, right? And this is actually the primary, this is actually the governing assumption that kind of governs how we perform RCTs. In RCTs, we randomize. So the idea is with that randomization is that we make it such that the statistical distributions of the treated and untreated groups should be similar enough. So it's really only treated in terms of at a distributional level. It's just the treatment that really kind of determines the effect. So this is why the randomization is really because this exchangeability. It really tries to exploit this whole concept of exchangeability, right? The next one is positivity, and this pretty much says that if you're going to do causal inference on observational data with covariates, you have to make sure that their subgroups, you can't just have a subgroup that just has all treated and all not treated, right? Which intuitively makes sense then, because like you can't, if everybody with a particular covariate set is treated or not treated, then you can't really say anything about them, right? In terms of the causal effect, right? So there's actually this interesting as well trade-off in terms of specificity and violating positivity, because and ideally you want to be able to specify covariates, right? To get, especially if you want to calculate the conditional average treatment effects, you want to be as precise as possible. But the problem is that if you get super precise, you end up to the point where you can risk actually violating positivity. So it's like there's this trade-off you have between specific and actually ensuring positivity is maintained. There's this trade-off there, right? There's also consistency, which basically say that if we apply a treatment, we observe the outcome associated with that treatment. So this kind of assumes like this is, this is, we have living in a deterministic universe, or at least at the macroscopic level, we live in a deterministic universe. So if you apply treatment T, you're going to get the outcome associated with that treatment on a particular treatment unit, right? That you're not just going to get the one associated necessarily with at least in that particular unit, they want to be associated with the control, for instance, if you assign the treatment. And next was independence. So the idea of independence is that no unit's treatment affects the treatment of any other unit. And this actually sounds simple enough, but it turns out that when you look at things in these sort of networked situations, these things become very, very hairy. So an example of this would actually be, let's say if you're doing, say, experiments on social networks, you have to be very careful with your design, because a social network is that what happens to one treatment unit might actually affect other treatment units. And that was going to corrupt your ability to actually infer those sort of causal quantities. And another example actually that actually gets relevant given current circumstances might actually be to some degree if you don't run, let's say, experiments related to vaccination well. Let's say, for example, you have a lot of households, and let's say everybody in those households enrolled in clinical trials, right? That might interfere with your ability sometimes to actually, depending how it's run, right? It really depends how it's run in that case. There, if it's not run carefully, it might interfere with your ability to sometimes make these sort of causal assessments. Right now, when you put independence and consistency together, it actually has this nice little name in the causal inference community. It's called SUTVA, or stable unit treatment value assumption. So when you combine these two, right? So when you take all these things together, right, we can actually under those assumptions actually make ATE the associational difference. So this is how you do it. It's that, okay, first you take the AT, and then now you have linearity expectation, right? And then you say, okay, let's marginalize out the X, and let's look at using the law of iterated expectation. And then what you'd use now, you use like independence, positivity, and exchangeability, and you actually get that third line there. And then lastly, when you use consistency, right? Because remember, that's a bit where we get the outcome associated with the actual treatment. We actually expand out to that last line there. You can see that how this is pretty much a associational difference with expectation, condition there on the covariate, right? So in a sense, we've taken this sort of causal quantity, and we see how if we can introduce these assumptions or make these things actually engineer circumstances such as these assumptions hold, we can actually then just apply associational difference to compute this causal quantity there. Right. So, when all the assumptions come together, with all their powers combined, you get the ability to kind of, make association causation. Right. So with that, let's talk a little bit about observational data to wrap up. So I say for well-designed RCTs are nice because it helps us realize those assumptions we just mentioned. But a lot of data is observational, all right? And sometimes they have to remain that way because let's say some experiments are very difficult / risky to perform. So for example, say customer churn, right? You don't want to deliberately sometimes do certain things that might actually incentivize customers to want to leave, right? Or let's say, for example, it's based off of like if you have this huge observational data set, like say millions of users from a social network, you don't want to forego that nice treasure trove of data and try to have like a small data set that's collected using more RCT-esque format, right? Some experiments are unethical to perform. So let's say, for example, smoking and cancer, right? You can't go up to like say you can't just say enroll a bunch of 18-year-olds in a study and say, okay, this half you'll smoke and this other half you don't ever smoke, and then like wait for 20 years and see if they develop lung cancer, right? That's not ethical to do, right? You can't do that. There are some interesting multi-arm banded type approaches that sort of like kind of like bridges this sort of gap a bit, but we won't talk about it here. That's more of a story for another day. But observational data is useful, right? Can be useful. We don't want to just throw that data away. So the idea is that how do we take observational data and find ways to kind of exploit these kind of assumptions for causal inference, integrate these methods such that we can get better estimates of causal quantities, right? Now, of course, these would not be perfect estimates of causal quantities because they're trying to kind of bridge the gap between the ideal circumstances and what we have, right? So the one method, and of course, this is probably the simplest method, would be these reweighing methods. So for those of you who've ever had the pleasure of working with an imbalanced classification data set, these methods would kind of seem kind of similar to you in terms of the intuition of how they work. The idea is that you basically reweigh different samples based off of their propensity to be treated. So the idea there is that, let's say, for example, if let's say seniors only make up 25% of a particular treatment group, you might say that every senior in the treatment group gets weighed more, right? And we need to create. So how we do is we have to create some sort of balance score that actually acts as the weight on that sample. I want this balance score function to be such that the treatment is conditionally independent of the covariates given that balance score. Our propensity score is a pretty popular method, especially in a lot of epidemiological studies. You find it a lot there. And the idea there is that how do you get this balance score is that you actually use a classifier, a binary classifier. So basically try to predict the probability of a particular unit being treated, right? And usually it's logistic regression. I have actually seen like random forest being used at least once, but I think primarily, at least what I've seen otherwise, it's really logistic regression based classifier they tend to use. And the idea there is that you use logistic regression classifier to get a score E of X for every covariate vector X. And what you do is that you can actually compute an estimate of the ATE using that expression there on the bottom there. So basically use this to reweigh samples based off of their probability of being treated. Right. So of course, E is bounded. Remember, we're assuming positivity here as well, right? So you can't have a probability of 0. Right? If you have a probability of 0, then this obviously would not work out because you'd have division by 0. But remember that as E grows smaller, it means that it actually causes the overall result to become larger, right? So the idea is how it kind of it weighs those samples greater because they're more rare in terms of estimating the AT. Right. Another approach is called doubly robust regression, this is where you actually do a propensity scoring, usually using the just regression as well, and then you use some other regression model to actually take into consideration the covariates as well as the treatment, and actually try to predict the outcome, right? And the idea now is, of course, these methods on their own are not enough, but when you combine them, right, you can actually kind of estimate what would have been the outcome in the counterfactual cases, right? And because trying to estimate what the outcome would have been in those counterfactual cases, you can apply this formula there to try to estimate the average treatment effect of the treatment, right? Another approach would be what I call matching method, the family of matching methods. So the idea is that, and this actually kind of uses some of the intuition here, like doubly robust regression. The idea is that we want to try to estimate the counterfactual outcome. And the idea there is that what you do is that you basically say that how if units are similar, then let's say, for example, if I have a group A, then I have a group B, and group A and group B are very similar, but group A is treated and group B is not treated, then their counterfactual outcomes should be the outcomes of each other, essentially, right? So for example, if Tom is a 25-year-old man in treatment group, and we want to kind of estimate what his counterfactual outcome would be, i.e. his outcome if he wasn't treated, we look at other 25-year-old men in the control group and we take their average outcomes to get a sense as to what Tom's outcome might have actually been, right? And then we use the formula directly that we saw above the Rubin model to try to actually calculate the average treatment effect. Right. Now matching methods depend on a notion of distance. So this is a very simple example. We just have like two covariates, right? Gender and age. But of course, like in real world circumstances, you would have more. So different ways of actually matching units with their counterfactual counterparts. Different metrics and similarity metrics. So of course, you have the Euclidean distance and Gross distance, which you would use, just the covariates themselves. There are also these transform spaces types approaches, like propensity score space. So what we mean is that we actually train a logistic regression model to get a propensity score, and then we match based on propensity scores, right? Within some sort of threshold, and we use that to match with the counterfactual counterparts. And you tend to find a lot, like when in public health literature, you'd see like when they use matching methods, they'd use these propensity score type matching methods, right? There's some work where ML actually is used here. So what you find in terms of deep learning, I should say, is that you actually try to do representation learning on the covariates, such that you transform them to a space where it's a useful space to perform these matching for causal inference. So sometimes deep learning is used as a sort of pre-processing step en route to trying to actually perform these classical causal inference techniques instead. Right. Another approach, and last one I'll just talk about briefly, is stratification / blocking. So the idea there is that you want to divide your treatment units into clusters using some sort of distance measure, a similarity measure. You can probably actually even apply clustering directly. So for example, you might want to take all the young people who are vaccinated with a particular vaccine, a COVID vaccine, and then you group them, and then you look at the treated, untreated basis. Say for example, a drug, let's say a COVID drug you're going to try. You want to see the outcome of the COVID drug across different groups, etc. And then you do that, and then what you do is take a weighted sum of those sub quantities, and that'll give you the population estimate for the for the average treatment effect. Sometimes you kind of nest these causal inference techniques in one another, so you can probably actually even do like say a matching methods or propensity based weighting or doubly robust regression in the context of the clusters themselves. So that's another approach as well in terms of being able to, let's say, trying to get estimate of the average treatment effect. So with that, that takes me to the end of my brief tutorial. Any questions?
Yeah, nice presentation, Inzamam. I have no questions, but in terms of the sort of applications we do, I mean, working on industrial problems, I guess this level of detail is probably not warranted, or doesn't, you don't need to worry about these things because the error incurred would be sufficiently small. Is that right?
It would sort of depend really on the overall problem. So I guess it'd be like, we have seen this in using data science is sometimes uplift modeling. So the idea there is, if maybe I should have actually mentioned this as a use case directly in the presentation. So like with uplift modeling, the idea is that you train a model to predict which customers might churn, and that's like the first phase. And then like in your second phase, what you do is that you want to have some ideas of what you can do to try to retain the customer. So you basically do that. You actually you actually provide an intervention, and then you record the outcome of that intervention. And then what you might do, you might then use the causal inference to again get a sense of like if the intervention actually worked well in terms of reducing churn. So like sometimes it's used, sometimes you tackle on the standard data science pipeline, and then from the output of that, like things like uplift modeling, then you can then tackle on another set of like rules, and then you can use causal inference to actually help gauge how well this actual process is working here. And then from that, you can then design better processes, etc.
Right. So but that's kind of deploying something and seeing the effect in the future, right?
Yeah, in a sense. So it's actually more used like when you're doing things, I guess, like process change, perhaps.
Right.
You can say like actually checking the effects of interventions themselves. Because no,
go ahead.
But I was just because like the idea there is to some extent like if like your like say classification model says, okay, these are high risk churners, then there's a risk of, I guess, a sense of misattributing to some degree some let's say for example it turns out that you try to offer the churners a higher discount, and it turns out that more people with the higher discount end up churning. It can sometimes be a case of depending how the pipeline end up kind of going, is like these are people who would have kind of like churned anyway. So but like it turns out that the discounts do help enough at least that it might make sense to still offer it. So like it has like those kind of confounding kind of situations there that it can be helpful in. But I mean, for the most part, it is sort of like a niche tool. At least for a lot of the work we probably end up doing, here.
Well, basically the issue tends to be the following. Like if we propose something for a company, they want to estimate the cost benefit trade-off to determine whether to go forward. They don't want to, they don't want to take the risk of deploying something that may or may not work. So you have to quantify the benefit based on historical data, and that could be tricky, because if you're using historical data and you try to see what would have happened if you had used your algorithm, then you have so many assumptions to make. And we've done it in the past. We've looked at certain metrics that we try to maintain the same kind of structure that would have happened if we had deployed the new algorithm, and see what the outcome would be in terms of those metrics. But yeah, it's a tricky thing, and that's where modeling and all these things is a lot of creativity. It's not just the algorithms. The algorithms are pretty much straightforward, but coming up with the basic design. But yeah, also in terms of even going forward, you know, the risk trade-off, you know, so we would recommend typically gradual changes and seeing so it's a feedback loop. You make, you know, where you want to go, but you don't want to go there directly. You kind of go there incrementally and see the effects so you can make changes along the way. But nice, yeah, interesting.
Well, I guess in terms of the actual measurement of possible outcomes of things, actually, that I've seen a particular business case of actually related to training as well. Is that they actually found in one case, with I can't remember which company it was that wrote about this, is that they realized that the customers that reported bugs ended up being less likely to churn. So, you know, like if you just kind of like if there's I guess a kind of blindly like applied it, it'd have been like, well, we shouldn't fix our bugs because if they see more bugs, they're less likely to churn. But like the causal inference was like, okay, well, what really happened here is that the time spent on the app confounds the number of bug reports. And because of that, it turns out that people who it's really the more usage of the app itself is really what reduces the likelihood of churn. So, I mean that's I guess one case there, but that sort of thing. Like, you know, something I guess like, you know, sometimes it could be a bit misty. It's just like run like just run-of-the-mill like regression on something sometimes.